So good afternoon, everyone. Thanks for being here on time again. So now I have the pleasure to introduce Dr. Claudia Mendes de Oliveira. Claudia is here from the Astronomy Institute, our department. She's a researcher on extragalactic astronomy, in particular systems of many galaxies, compact groups, fossil groups, groups in general, outskirts of clusters. And in particular now, she's leading an effort to build instrumentation in our institution. She's as well a very active member of the GMT-Brazil consortium, and now she is our representative on the GMT board of directors. And she's going to talk about what our efforts on the instrumentation are going. Thank you very much, Claudia.
Okay, I'm going to talk about the optical astronomical instrumentation in the state of São Paulo, some history, and our advances in the past few years. I will divide this talk with Rafael Ribeiro. Rafael is going to talk about the GMACS in general, and specifically about the optical design of GMACS. So I will give half of the talk, and he will continue after that. So I already have a problem. Eu quero ajuda porque eu não vejo, né? Só ligar. Okay, the institutions of the state of São Paulo joined GMT in December 2014, with FAPESP being a GMT founder member. And this represented a new opportunity for instrumentation in the state of São Paulo, the same way that 20 years ago, entering SOAR and Gemini was an excellent opportunity for LNA, our National Laboratory of Astrophysics, to also make a great advance in instrumentation. So in São Paulo, we are 42 million people, so 20% of Brazilian population. We are responsible for 32% of Brazil's GDP. We produce 45% of the Brazilian science in all areas, of course. 39% of the PhDs graduated in Brazil are here in São Paulo. 13% of the state budget goes for higher education and R&D. And 1.7% GDP goes for R&D. This data is from Director of FAPESP, Brito Cruz. And in São Paulo, we have the great luck to have FAPESP funding our research. So as Dr. Shamovich said in the first day, we can plan things because we know exactly how much money will come to this foundation every year. So this is really a major difference. And that's why all the astronomical instrumentation, also those that were fabricated and done at LNA, were led by São Paulo PIs. Okay, so we cannot talk about São Paulo instrumentation without first giving an overview of what is done at in Brazil, and specifically at LNA. LNA is this laboratory that is about 5 hours drive from here up north. It's in the state of Minas Gerais. And it's our main instrumentation center in Brazil. The main research institutes of astronomy in Brazil are spread over the country. We have 61 institutes or universities in Brazil that have one or more astronomers. And among them, there are two that are directly linked to the MCT, which is INPE, our National Institute of Space Research, which is 180 kilometers from here in the state of São Paulo, and the National Observatory in Rio de Janeiro. Our national facilities are 6.5% in Gemini, north and south, so 2 telescopes, 8 meters. The 4.1 meter at SOAR, we have 34%, and we exchange time with Blanco. So we have access to 8 meter and 4 meter telescopes. This is quite important for our community. OPD is the Observatório Pico dos Dias, which is owned by LNA, so it's in the south of Minas Gerais. It has 2 small telescopes, 1.6 meter and 0.6 meter, that are still working and used by people to do science, but mostly now for students and also for testing instruments. And we have a very recently T80 South robotic telescope that is doing a survey in 12 bands, going as deep as Sloan in the southern hemisphere, 8,000 square degrees. This has started about 6 months ago. And in the future, we're going to have a robotic telescope of 1 meter in Argentina, in collaboration with Argentina. So the National Laboratory of Astrophysics is the place that operates our telescopes, so SOAR and Gemini, and also has a very good infrastructure for instrumentation, specifically for fibers. I'll talk a bit about this, and a metrology lab, among other laboratories. But so they have been growing the last 20 years, forming people. It was a long process, but it's well established now. So this is instruments by leading institution. The blue ones are the ones that I'm going to focus, and I'm going to use these instruments and the history to tell you a bit about instrumentation in Brazil and then in São Paulo. So LNA is the only institute here that's not in São Paulo, and I'm going to talk about the instruments so that you can see a bit of the history and the advances there. And then INPE, IAG, and IMT. IMT is Mauá Institute of Technology. It's a group of engineers, very good at software and controls engineering, and they are part of the GMT consortium as well. So I start with CIPS and Stellis. These were 2 spectrographs that are built by Brazil and will become community instruments at some point. They are in tests right now. CIPS is more advanced than Stellis because it started earlier. And this history here, I'm not going to read everything, but just to give you an idea, this is an IFU spectrograph, so for optics module mounted at the optical Nasby focus, and a 14-meter long optical fiber bundle with 1,300 fibers. Of course, this was built with fibers and technology of the end of last century, so it was done today. It would have been done differently. But still, the new results that came from last month seem to show that this will be an important instrument for the community, and it will be offered as a shared risk in the next semester. So the resolution is 5,000 to 30,000. It uses VPH gratings. And the decision on making this was in 1999. So a group of astronomers sat down, since we are mostly spectroscopists in Brazil, and it was felt the need to have a spectrograph like that. But we had no people, we had no labs, we had absolutely nothing. So we really had to start from beginning. So we found 2 people, sent them abroad, one to AAO, the other one to the CTIO. So these people came back, they were hired by LNA. These people started the new labs. With SOAR, we then got some funding from FAPESP to start this spectrograph. And everything went quite slowly, but surely this helped a lot to build the expertise of instrumentation at LNA. This instrument was finally taken to SOAR in 2010. It had some problems in the transportation, also some problems with the fibers when it was there. Finally, in 2017, it's been commissioned in a successful way. So just some pictures of the lenslets that are used. Another thing that is interesting that was designed here, it used the companies in the São Paulo state. And this is the bundle of fibers here with the 1,300 showing one lab in LNA. This is the, I would say, the lab that has really international recognition, and these people are now also working for the Subaru telescope, one instrument of Subaru. So this is a very nice lab at LNA, and the motivation to create this lab was this instrument for SOAR. So these are the first results for M83, the center of M83, the first data cube taken. And data were taken for 5 PIs. It was distributed to these PIs, and now they are waiting for feedback, but apparently everything is okay, and they are going to open to a larger community in the next semester. Okay, so the second spectrograph is called Stellis, also built in LNA. The PI is Bruno Castilho, the director of LNA. It's the SOAR telescope shell spectrograph with resolution 50K, maximum of 80K. Very nice thing about spectrograph is that it has no moving optical parts, a fixed configuration, and you can get optical from 300 to 900, so very good blue transmission in one shot. Uses VPH gratings. This has not been in the sky yet. This is just a design. It's not the instrument. It's still in the lab. You see, you can get to all parts very easily. So it was a nice design. And this is just a spectrum of sunlight because it has not been in the telescope yet. It is in tests in SOAR. I saw it last week. So it's mounted and aligned at the SOAR lab and is ready to be mounted on the telescope and tested. So these are 2 new instruments that may enrich the group of instruments of SOAR and are very necessary for a long time. The community is eager to use them. So we hope that it will be successful. Now, LNA also is building part of an instrument for an 8 meter. In fact, this is new to us. We have had now 3 instruments for 4 meter, no instruments for 8 meter. So this fiber cable for the prime focus spectrograph. Roderick yesterday talked a little bit about the science for this instrument. And now I'm just going to show you what is being done in the instrumentation part, in the technical part. The PI of this instrument is Professor Laerte Sodré Jr. from IAG, but it is fabricated in LNA. So these are the 3 cables, optical cable A, B, and C, that will go from the top here, where light comes from the wide field corrector optical interface and goes to the 4 spectrographs. This instrument is going to have 4 spectrographs. And these cables are the responsibility of the LNA to fabricate them, to make them. It's very careful work with the fibers. They try to make a connector. The connectors that connect the cables, the several cables, is something that is really important because you have to have an efficiency that is quite high. So they also prototyped some connector, dynamic connector with 600 fibers with a good throughput, but in the end, this is not going to be used in this instrument. But it's nice that they also could do this prototyping there. They also do a lot of tests with the so-called Cobra fiber positioner. They have all the test benches to do this kind of things like focal ratio degradation, twisting, and torsion tests of the fibers, simulating expected conditions. So they do this all in LNA. And they were very proud that they were able to do this curved slit for in their labs as well. They also work with composite materials, so it's quite a successful lab. Finally, I just want to mention that LNA still builds instruments for their 1.6 meter for the community, and they are building Spark 4. I wanted to say that because Claudia Vilega from INPE, this Institute of Space Science close to here, is the PI, and it's a nice work. They are starting fabrication of this simultaneous polarimeter and rapid camera in 4 bands. And this is for the 1.6 meter telescope. So with this, I finish my part of LNA work, and I would like to come back now to São Paulo, what has been done here and what we plan to do here. I would like to repeat that this is really a great opportunity for instrumentation for the state of São Paulo. Why? Because we entered the GMT with $40 million. FAPESP is paying $40 million in 8 years. And in addition to this $40 million, FAPESP gave funding for advancing instrumentation, and this is our goal in the next few years. So we work together with several partners in the in the state of São Paulo, and we work in a way that this funding is both for buying hardware, for software, and our partners will contribute with people, because they have an easier time than USP to get the people. So with this, we are able to get several engineers, which before we didn't have access to engineers. We only had one engineer at IAG, and now we have access to several engineers. So it has been a very productive way to work in a group of universities. Okay, so this funding that is coming from FAPESP to advance in instrumentation is not only for IAG, not only for University of São Paulo, also for other universities. I give you an example here of UFABC. Marcelo is here, and this is a slide that I got from him. They also just inaugurated their laboratory for adaptive optics for the GMT project with this funding that I'm talking about, and they are characterizing the wavefront, both with wavefront sensors and photomultipliers, and they have many plans to enhance their capabilities there. And here at IAG, we also inaugurated 4 labs last year. And this is just some pictures of the optical lab at IAG. I would like to invite you, anybody that would like to visit the lab tomorrow at 10 o'clock. There will be a tour of the lab and of what is being done there. I will be describing a bit here. We have to special thanks to Dennis. Dennis has been our only engineer for many years now. Of course, we have more, but he did a great job to help equipping these labs. So I'll talk a little bit about what is being done in the labs in the subsequent slides. So the main work for our lab right now is SAM+. So SAM+ is an upgrade of the SAM instrument. So SAM is a SOAR adaptive module that works very well in SOAR for the last many years, more than a decade. Oh no, more than a decade, no, sorry, since 2013, so for a few years. And we hope to do an upgrade of this instrument. So SAM is, as I said, the adaptive module of SOAR, and it corrects ground layer turbulence using an ultraviolet laser guide star. It has been commissioned in 2013, and it's on operation since then. It has an imager, it's called SAMI, a 3x3 arc-minute field. And very recently, we put a Fabry-Perot there. I will show you some results of that. It does a good job in the I band. It's much less good for close to 5,000 angstroms, for example. So the idea is to refurbish this system. And we have several people here in São Paulo working on that now. So this is just some images taken to show how it is stable over the field of 3 arc minutes. You get good images everywhere. And you can regularly get 0.5, 0.4 arc second seeing from a 0.8 arc second with half max, or the opposite. So what is SAM+? It's this upgrade because although it started work in 2013, SAM is from 2003 or so, from technology from the last century as well. So it uses a bimorph deformable mirror, beam 60 from SILAS. We can get something that's much better now, larger, with more actuators, and also a small CCD. It's so only to the limited number of DM actuator. This correction is never perfect, especially if it's not in the I band, more to the shorter wavelengths. So the AO technology available today will allow us to increase the correction using the same laser. So we can just change the DM and the wavefront sensor for more modern components and get a much better instrument. And in fact, this is going to be very good for Fabry-Perot and also for SIPs, because we are going to use both instruments with SAMs. So you fix one instrument and you get others also for free. So this is the idea. These are the main components suggested for the SAM upgrade. This here, you see it's 241 actuators. It's also more like a square version. The other one was a radio version. So you have a larger number of actuators and a gated CCD with more micro lenses. So this will do a much better job. And this is just a comparison between what it is now and what it's going to be for bad seeing. And this line here is under good seeing, you get a much better correction. About 2 gain in stereo ratio for good seeing with the SAM Plus as compared to the SAM as it is now. So these are, of course, simulated improvements, simulated results, but we hope that it will work better. And also right now, SAM works with Shark Hartman, and our group is planning to test if Pyramid will be better. So this is a good work to get the lab started, and it's also very useful for the observatory. So it's a collaboration between São Paulo and Tololo. The idea is to have a conceptual design review in a few months, in fact, and the commissioning by late 2020. And this is the slide given to me by Daniel. Daniel and Tássio worked on this. They went from nothing in the lab, no AO, to closed loop in about 10 weeks. And there's a very nice movie that shows the result of this experiment that I decided to not put here. But if you go to the tour tomorrow, you can see also the movie showing how they were able to close loop with this the system for the SAM Plus experiment. So I now go to SAM Fabry-Perot, which is a part of SAM. So it's just a device that we put inside SAM. When SAM was made, it was left a space in the instrument, which thanks to Gerald Cecil, who said, no, just leave the space there. Maybe somebody will want to put a Fabry-Perot there one day. And when we discovered that, we thought, this is great. We were using BTFI at the time. We were not able to put BTFI or with ground layer adaptive optics. We wanted to have access to this unique opportunity of having velocity fields done with ground layer adaptive optics. So we wrote to Matthew Collins. We asked him his his etalon that was borrowed for a long time. So we are using 2 etalons, in fact. We borrowed one from AAO. We borrowed the other one from Maryland, from Sylvain Veilleux. And we've been using Fabry-Perot inside the SAM. So this is wonderful. We transformed something that was just imaging to spectroscopy capability. So this is a Fabry-Perot, thanks to Andrew. He explained everything, how it works this morning. So it's a sandwich of glass, no? And you have interference, and you have constructed interference for some wavelengths. We work here with 2 Fabry-Perots. One of them is 12,000 resolution, and we just scan. Scanning means changing the distance between the 2 plates to measure the line of H-alpha. So we just measure the position of H-alpha for the 12,000, and the one that we got from AAO, we get 3 lines, so the 2 and 2 around H-alpha. This gives rings because there is axial symmetry. So the single pixels will turn into rings, and we also give the data to the community already reduced, which is nice because it's quite complicated to reduce this data. And the one drawback of using Fabry-Perot inside the SAM is that we use the CCD instead of a photo counting device or EM CCD. So for the scanning, the readout noise of the CCD is not so good. But when this change is done to SAM Plus, then you will be much better for Fabry-Perot work as well. So this is the space that was left there, and we had just to put this, we had to make this, just design and make these things and put the Fabry-Perot inside. It's working with a controller that is 40 years old but works perfectly. We have 2 of them. This is a Queensgate ICOS Fabry-Perot. And this is some results. It's very nice results. Here's the velocity field of the antenna galaxy. Was the very first data cube that we got. This is a much nicer thing to show because it can really show the uniqueness of this data. This is data from VLT in black with a slightly larger, higher spectral resolution in black. And the red one is the Fabry-Perot, just to show that the results for the Tarantula Nebula are exactly the same, where you have measurements of both. But this is done every 20 arc minutes. And while with the Fabry-Perot, you get to image, you get information at every 0.2 arc seconds. So, for example, if you are observing, if you want to look for bubbles in this nebulae, that's the kind of data that you need. And you see that you need it because the profiles change in a very small space. So just this little square here has all this information with the Fabry-Perot data. So it's really unique for this kind of study. Also interesting for star formation objects in the nearby universe, like the blue nuggets in the local universe, is studied by Sheila Kanapan and her students. For study of planetary nebula is wonderful. People usually use long slits across several different position angles. And here you have one velocity field will tell you the whole story for modeling planetary nebula is quite interesting as well. And this is the one example I have here with the AAO, Fabry-Perot, showing the 3 lines. You can see here, the 2N2 and H alpha. For the center of NGC 1068, we are doing now just modeling of the several gas clouds inside this central region. So it's quite interesting. So for AGNs, this is the best Fabry-Perot to use because the line is quite broad, and this has a free spectral range of 2,000 kilometers per second. So that's what you need for broad lines or for objects that have a very large range of velocities. So we are really happy with this instrument, although the data reduction is giving us a lot of headaches, and that's why it's taking some time to give the data to the astronomers. We have had 3 early science runs. The last one was last week. That was totally closed. The telescope was closed due to high humidity the whole time. But the other 2 were very successful. We have a lot of data to give to the people. So now I come to very quickly to the multi-wavelength survey dedicated telescopes. We have been very involved with these projects in the last 5 or 6 years. Laerte Sodré Jr., myself, Raul Abramo, and several other people here. There are participants everywhere in Brazil, and these are 3 telescopes, 2.5 meter and 2 80-centimeter telescopes. And these telescopes are going to do some surveys, so that they are dedicated. So GMACS will do a survey of 8,000 square degrees of the sky in 59 filters. So it's like a low-resolution spectra of every object down to 22 magnitudes, IAB. And J plus and S plus are 2 smaller telescopes, 80 centimeter. And they are going to do surveys of the 8,000 square degrees in the north and the south to the limit of Sloan in the broad bands, and using several other bands which go on top of the main features of stars. So H alpha, magnesium, 4,000 angstrom break, O2. So very interesting narrow bands. So we are going to see the very large areas of the sky, for example, in H alpha. That's something that is quite unique. This is just to show, is the only slide I'm going to show you of JPass, except for one for the science, but just to show you that the camera of JPass is ready. So these are 14 CCDs that are 9K by 9K from E2V, 10 micron pixels. The camera is ready, and this project is probably going to start at the end of this year. JPass is very competitive in all canonical dark energy probes, BAO, supernova type 1A, cluster counting, weak lensing. So it's an unique data for a range of sciences from solar system to cosmology. This is the kind of thing that we're going to get with the 59 bands. Yeah, so it's like really like a low resolution spectroscopy. And so beside the 250 that you do JPass, there is this small telescope that you do J+. And J+ has been working for 2 years. So we have had lots of results from J+. I don't have time to go into them here. I'll just show you some examples of things we got at S+, which is the same telescope but down south. The only difference between them is that the southern one has a polarimeter. So there will be also a polarimetric survey, which is quite unique over a large area. The PI of this instrument is Antônio Mário Magalhães, here from IAG. But other than that, the two telescopes are identical. The camera, everything is the same. So this is T80 South in Tololo. So there's one in Spain and another one down south in Tololo. This is the telescope and the field of view, which is quite huge. You can see things in the scale of clusters, scale of galaxies, scale of the bulge of the object, and the pixel scale is 0.55 arcsecond per pixel. So these are the filters. So you compare with SkyMapper and Sloan, you can see that for things like searching for metal poor stars, the fact that we have this very narrow band are very interesting for a number of objects, including searching for metal poor stars. For photosys, it's very important. For IFU science, for trying to derive different stellar populations for different parts of galaxies. So even when Type 1 comes and you give spectra of all these galaxies in the southern hemisphere, we still have some space because that will be a fiber in the center while we will have information for the whole galaxy. Now, finally, GMT-related projects, and I'm going to soon pass it to Rafael. We have currently the following projects within the scenario of GMT: systems engineering for GMACS, optical design of GMACS, software architecture of GMACS, manifest interface with GMACS, and AO experiment for GCLEF, which Andrew explained this morning at the question-answer session. He explained this, and I will explain again quickly. Okay, so these are the people in the GMT-Brazil office. We have 28 people. So, for example, I'm here, João Steiner is here, there's some senior people, but 14 of these 28 are really young people, young engineers, that are here to work for GMT project, okay? So these are systems engineer people, optics, optomechanics, software, and they are eager to engage in instrumentation. We also have 2 graduate students, 7 undergraduates. And we have main partner institutions, the IMT, the Mauá Technology Institute, Univap, which is close to here, 180 kilometers, UFABC, which is about 70 kilometers from here, and LNA is always our partner, of course, because this is for the whole of Brazil, and so also helps São Paulo. Just to give you an idea, these are 4 very recent hires. Now we have Renato Borges, a software engineer, worked in Paris and in Marseille doing data reduction with astronomical data, and now he's helping with GMACS, just starting. Márcia Beatriz, a bachelor in computer science, master in electrical engineering, PhD in computer engineering, and also working in the project. Antônio Braulio Neto, mechatronic engineer with experience in mechanical design, 3D modeling. Tássio, which is his master and PhD in applied optics. All these people, when they applied for these positions, they had lots of other people that also wanted the job. They are just the best ones. They're really, really good people, and we are really, very glad to have now the team that we have. I think that we are really ready to make a big step. And also we have some students, for example, Henrique Volpato is doing his master's degree, and this is the experiment that Andrew described this morning, trying to maximize the light inside the fiber of GCLEF and also check for stability. And this is done by simulating AO or just natural seeing, and it's done in the lab, in our lab, optics lab. They can also be seen tomorrow if you like. And you have another Henrique Ortolan, who's also a student of ours, that is now at AAO for 4 months, and he is working the concept of manifest because, as Matthew explained this morning, Type 1, the star bugs come from the top, so gravity helps, right? But manifest has to look at the secondary from below, so the star bugs will have to come from below. And he is working in these tests of really making the star bugs go upside down and how to do this change. He'll be there from February to June, and it's a very good experience for him. He really likes it. Yeah. It's called the invert bug catcher. It's the security way to not allow the the star bugs to fall. No? The Instituto Mauá, their forte is software and control. They have worked in Corot mission, development of signal processing algorithms. They also work in the Plato mission. They are actually working right now, and they are working for an ISO instrument in phase A. So they are also very willing to help with GMT instrumentation and to form students. Systems engineering is one of the major areas that we are now working. We have a team of 5-6 people in that. We have an advantage because UFMG has a 6-year undergraduate course, which is very good. It's an excellent source of professionals for us. And INPE also is an excellent source of senior professionals because it's, you know, Space Research Institute that has been using systems engineering for some time. Systems engineering is just a field that will take care of the project from the very beginning to the very end, specifying everything you need. GMTO has strongly recommended that all instruments fully integrate into their GMTO systems engineering system. So we are really hoping that that we are going to be able to help the instruments in that area. Right now we are in GMACS. So this is our team. We are helping with SAM Plus. GMTO receives Aline 2-3 months per year, so she's helping there. GMACS and Manifest. We are very happy with this team. And the team responsibilities in GMACS are application of GMTO Systems Engineering Management Plan, requirements management, risk management, and operations concept description document. And they also share some responsibilities with project management. Just to give you 2 examples of things they do, so they look at every single area of the processes and also every single area of the work breakdown structure. Okay, so now I will pass it to Rafael, who will talk about the GMACS and what he's doing in the optical design.
Okay, good afternoon for everybody. My name is Rafael Ribeiro. I'm an optical physicist. Oh, sorry. Yeah. And I'm a PhD student here of the astronomy department. And Claudia is my advisor. Okay. And I will brief in these 20 minutes, I will try to say about something about the GMACS, the brief cranks project status, and a little bit of what I'm doing here about the optical system design. And about some science instrumentation requirements as well, and in the end, some methodology, and one trade-off case that I'm facing here. Well, first of all, GMACS means Giant Magellan Telescope, so it started with G, it's a good start. So it's a multi-object astronomical and cosmological spectrograph. So it's a spectrograph. It's not intended to have a image mode, but it can have one. And it's a multi-object as well, so it has the features of the multi-object, so it can get spectrum of multi-object, and astronomical and cosmological approach. The GMACS science drivers here for the project can be stated in a few sentences. For instance, it must have high throughput. So the idea here is to get some light for very faint objects. It will have a simultaneous wide wavelength coverage that gets all the visible range. And we'll have a correct and precise sky subtraction as well, so it can go further in the time in red shifts. And with moderate resolution, that it goes from 1,000 to 6,000, 5,000, something like that. And of course, we'll take all the wide field that is for extremely large telescope is the 10 arcs minutes wide field. And it's for spectral range. And I got the sentence here from the GMACS Science Requirements book that says that a spectrometer that operates in the visible spectrum with the capability to observe multiple targets simultaneously is critical to our goals in this vast area of application. For instance, star formation, star population, and most of the extragalactic science. Indeed. there's more information here available on this website of the Instrumentation Lab of the Texas A&M University. But here's just one example of what the GMACS science can be, what was the science that GMACS can done. Some of them were described in the last meeting here, and more of them can be used for the integration of the manifest as well. So it's a very versatile and very multi-purpose object instrument. Okay, the GMACS here is a GMT, of course, and GMACS will be placed on the Gregorian instrument rotator that is right on the Gregorian focus. Here's one of the design that shows the dimension of what will be the GMACS, which comprise the 2 cameras and the collimator. Okay, the principal functional parameters. These principal functional parameters were results from a lot of discussion of what a spectrograph should have to accomplish all of the science case that I showed. So here there's 2 columns, the requirement columns and the goal columns. I would say just pay attention to the requirement right now. So it's a field of view of 30 arc minute square. Okay, the wavelength coverage gets from the 350 to 950, and the spectral resolution for both blue and red arm, which will be defined. There's 2 range, so it's 2 modes of operation. And some image quality here, that is 80% of square energy at 0.3 arc second. And there's some mechanical here parameters with the spectral stability, that is 0.3 spectral resolution elements per hour for such a large instrument. It's a big challenge. The number of gratings will be 2, so we can tune different gratings for each camera. And the slit max exchange will be more than 12 here right now. And here's what they say that is goal. Goal would be a desire, one thing that will require more than what we know to construct, and we will need some challenging to be achieved. Okay, the first order of parameters stood once we get that requirement, that is a few numbers of requirements, so we need to get some number for that. For instance, once that we have the telescope F number, that is an input from the GMT, and we have the maximum pupil size as well, that is a constraint from the suppliers. Suppliers has some constraint about the diameter they can manufacture the gratings. And the resolution which required, we can get 1 collimator focal number range that will go from 2 to 2.5 meters. And once that we have the spectrograph field of view, that is a requirement as well from the GMT, and some known detector spectration with the typical camera design that is used for such large spectrograph. We get 1 maximum of camera field of view, which is 22 degrees, is a kind of large field of view. And when we have the physical size of detector arrays, that is limited by the suppliers as well, and the camera field of view, we have the focal length of the camera. So with that numbers, we can now describe the high-level description of what will be the GMACS. GMACS will be a dual beam volume phase holographic gratings. It's one special kind of grating in a CCD spectrograph. It was a 1-axis single collimator up to now, so it's just 1 single collimator with high throughput. So this is what I would like to remember about GMACS. It will be a high throughput system compared to other one. And unfortunately, some articulated camera as well. So this large instrument will have some articulated parts of it. And here what I call it the blue and the red spectrum, which is defined by the dichroic and the gratings. So it would be from 320 to 550 and 550 to 1000, the spectral range. And CCD cameras, of course. And therefore, with that previous numbers, range of numbers of primary numbers of the optical design, we froze some numbers to start the design. So the collimator focal length is 2200 millimeters with the f8.1, that is the GMACS, the GMT aperture. The camera's focal length as well is almost 600, and exit pupil is 270 millimeters. That number here comes from suppliers' capability because the grading will be tilted, so it will be much larger than that. And the slit length that is the field of view of the collimator is 7.4 arc minutes, so it's a long slit 7.4 arc minutes. which will give in a circular field of view of 42 arc minutes square, with a slit width of 0.7 arc second. That is roughly 200 micrometer on the detector plane. This number here is linked to the manifest. Detector format will be comprised by a mosaic of 2 by 3 of 4K square CCDs at 15 micrometer the pixel size. Okay, and there's some reconfiguration options of the GMACS as well. There is a good capability of this instrument that we can have a wide range of volume phase holographic gratings, which can be replaced in a short time. We expect that it could be replaced for better wavelength selection. And with the grading plus narrow beam of filters, it can allow high multiplexer observation with narrow spectrum features, up for single or multiple spectral lines of many targets. We can even replace the gradient with a prism, which will give more throughput but very low resolution. It can be used for some side case as well. And it's possible to have narrow band for image mode, would be a band about 20 to 30 nanometers of distance of spectral range here for all the GMACS spectral range. And we are not expecting to have polarimetric mode for the GMACS itself. Okay, it can be done by manifest maybe. Here's some pictures of the on-X GMACS field. So here we can see the cameras that is located in some circular trail, rain trail that can be movable. Okay, for select different modes of operation, the let's say high and low mode operation for both cameras. There will be some devices here to change the filters that can be selected some specific waves. Okay, here this mask is here. The mask will be located here that can be totally automatically placed on the focal plane of the collimator, actually from the telescope. And here's a field lens. It's a big, huge instrument. And remember that all this instrument here will be attached on the telescope bottom. So it will be moved with the telescope movement as well. And of course, it will bring a lot of problems. Some of them is about the gravity and thermal-induced deflection and stress that we can cause. So here is some FIA, finite element analysis that was performed in the previous design, which shows where does all these structures change. So it will affect directly the spectral stability of the lines. And here as well is some study that currently will have some problems in the space envelope, which in this configuration here will require one space of the external base. To overcome these problems about the deflection and thermal load, we use some hexapods. Hexapods is an excellent device that can compensate for this deviation caused by deflection. It will be located in the cameras and maybe even the collimator as well. That will be fully integrated in the control system of the GMACS. Some shutters for the cameras itself, and here just one shot of one highlighting how it will be the dichroic here to feed both cameras. Here's the base configuration and what we think right now about to use with manifest. Okay, here's the GMACS in the direct Gregorian position, is when it's operational, straight. Here is in the green shows the GMACS storage bay when it's not used, straight on the direct Gregorian focal. But manifest can be fit here, and then manifest can feed the GMACS in this position. So the idea is that all this structure here will be moved to its storage bay, which can be which will be done by some trails, rain trails, and only when the telescope is pointed to the zenith. So no stress can be done, must be done. Gravity stress will be done when it's moving. Okay, now it's some ideas I would like to share with you about the optical design. How does it work? So remember that we got from GMTO the functional parameters of this instrument. That comprise 6, 7 numbers. But when we put on the paper, when we need to develop an optical system of it, it requires more than that. For instance, we need to check the focal length, trigger at the focal length, FAC number, the aperture. Wavelength spectral range is one thing that is inputted. But what kind of type of lens we will use, the definition and we need to define the back focus, the front focus, the pupil locations as well, some problems about illumination. Eventually, we need to characterize for ghost image, for distortion, subvariation with conjugates. Fortunately, there's no zoom, but all the range of image quality to measure for aberration, for resolution, optical transfer function, energy concentration, some scattering lights, polarization issue. There's some mirrors on the optical path, some light baffle. There's a huge number of things here. Diffraction effect, tolerance, that is very important, deep of focus as well. The cost of production, cost of line, there's a lot of things that we need to figure out. So it's not straightforward to go from some lines of requirements for a complete optical system design. Okay, there's more here, and now it's all. Fortunately, we need some system. We have some system engineer and some methodology to go through all the steps of development of the system. So the complete system is comprised by the camera, by the collimator, by the gratings, that can be optimized individually. So we call the subsystem optimization. That starts from there, from the GMACS, from the GMT requirements, science requirement, the GMACS proposal, which then can be split for the blue, red, and collimator optimization. All of them must meet some requirements, which we define. Therefore, in the end, with the integration of the spectral as a whole, we must meet the requirement that is the instrument requirement itself. So along the path, we have the optical mechanical inputs, okay, and some integration. Yes, the optical mechanical inputs, and maybe sometimes that it appears here, some changed requirements due to some strategy from the GMTO. For instance, that is one case study I would like to point, is the single change the requirement from the 350 UV cutoff to 320. What does it mean from the optical point of view? So this small change will cause, for instance, this constraint. Here's one map that we use a lot in the optical design. That is the ab diagram, which shows each point here is one different glass that we can use for optical system. Here's the index of refraction for a specific wavelength, and here's the ab number. That is a measure of the dispersion of the glass. So higher is this number, here is lower the dispersion. Okay, so we can have a set of more than hundreds of kind of glasses to use for a ordinary optical system. But it decreases a lot when you have only two restrictions. One is large blanks. The suppliers must provide the large blanks for these large lenses, and internal transmittance as well. So all those more than 100 glass now are limited to few 15 glass. And when we require that they must have a high throughput for 320, we have only two glass. That is a calcium fluoride and fused silica. So it changed everything in the optical design. So we need to redo a lot of work. For instance, here's the what we call the panchromatic collimator, panchromatic because it gets a lot of all the spectral range of the GMACS. And it has the field lens. It's a lens that more for 400 millimeters, and it's comprised by field lens, one Nikon glass, calcium fluoride on that. And unfortunately, there's a kind of drop here in the throughput only for the collimator. The cameras get larger. So here's this gradient here. It's not allowed for a 320 high throughput. So the idea is just to make it straight line. So we need to figure out another way to do that. So only with this change on the requirements brings to another totally completely different concept for the collimator. The idea is very good for a science case. We will be one of the maybe unique instruments to go deep into UV 320 with a high throughput. Okay. And here's the perspective of the camera as well. Here's the camera that we have, and here's a new camera with had a new features that was provided by some previous feedback. Of course, these constraints here were included to avoid some interfaces between glasses. All of the interface here is a large lenses, and one lens that is in contact with the other one can have some problems when it's thermal loaded with tolerance as well. So we decide to make all of the doublets and triplets like air doublets and air triplets. So there's no only singlets that make part. We'll have some parts here for mechanical envelope as well, for mechanical space for filters and shutters. And we include some optical tricks here for vignetting. Okay, so in conclusion, the GMACS project is in progress, of course, and in the optical point of view, we are now in the trade-off analysis. For those who are not familiar with trade-off analysis, it means that we have one problem and then we'll have different possible solutions for that. And instead of just choose one, you need to list all the advantages and disadvantages of all of them. And all the consequences of that choose we'll have in the future in the project. So there's a lot of kind of trade-off analysis. For instance, to decide between refractive or reflexive optics for the cameras, the collimator architecture, the dichroic transition wavelength with where is the best position for the transition, the vignette on camera, what the consequences on the throughput of it, and some lateral color effects here on the spectral, etc., etc. So we're performing all of that. And right now we have the optical system that is in a baseline, a standard baseline for further optomechanical analysis. And this is an invitation that we are going to be at Texas, Austin, for the next SPIE meeting. So not only the optical sub-project will be there, but all the system engineer, electronic, and the system as a whole. And that's all.
Thank you, Rafael and Claudia. So, before giving you the word, before Rebecca had to leave before, and she apologized for that. But before she left, I asked her if we can have an imaging mode on GMACS. Because an imaging spectrograph, if you take off the grating and put a mirror, it becomes an imager. The project was not very leaning to that, but now they are happier to have one as well. So that's good news for the one that wants some imaging.
Actually, Eduard, we don't need to put the mirror there. We just use the straight position. So in the low mode, you just straight a little bit because the trend allows us to do that. So it's one less reflection.
Sorry to keep bothering. Can you go back one slide?
Of course.
I had just your conclusion.
Yes.
Because I had already written my question because the optical design was very interesting for me, and when I saw this slide, I was like, yeah, question is perfect. How comes the collimator at the moment is a lens and not, for example, a mirror, which is the case, for example, of VMOS? Well, we heard is the instrument which doesn't work, but it's also the case on Osiris, on Grand Tecan, and that collimator works absolutely perfect. And
yes,
it's helpful to keep the instrument more compact. So.
Yes, actually, this is a trade-off analysis that we're doing right now. We have selected some design for a mirror-based collimator. One of them was a three-mirror astigmatic system, but it takes a lot of space. And one of the big restrictions was space. Okay, and another thing was to get the higher throughput as possible. So no collimator with obscuration was allowed at that time. So that was a two key statements for that. So it's the space envelope. We have some drawings over that, and to keep the high throughput.
Another question that I have. Sorry. When you mentioned at the very beginning, you mentioned that the instrument is for faint objects.
Yes. So,
can you give a feeling of what faint means in this context?
Yes. I would need some help with my friends here. The magnitude of the
magnitude limit of GMACS. Like, if I get a spectrum at the lowest resolution
what is the magnitude?
for example, 1 hour, what is the magnitude I get for a signal to noise of, say, 10?
Sorry, I think the requirement's 25 on R band, is lower.
Yeah.
But we are working towards the goal, then it's further. But the number that comes to my mind is 25.
Thank you.
More questions?
More.
Probably for Professor Claudia, I think, but if you can answer as well. I'd like to know how is the collaboration or the start or the state of art of the industrial partnership here in São Paulo to work on those instruments. Because in your slides you talked about institutional academic partners and about the industrial commercial partnerships.
Okay, so you give me the chance to say something that I forgot to say, that when FAPESP agreed to pay the $40 million for GMT, we had to sign a document between the rector of this university, FAPESP, and us as the people who will make this happen. So the university will give some positions of professors during certain years, and that's why we have Alessandro here now. FAPESP does its part that pays for the telescope and gives us funding for the instrumentation. And we have the task to involve the São Paulo industry, not only in the fabrication of the instruments, but also in the fabrication of the parts of the telescope. Yeah, this is actually quite hard because, of course, everything is it's a competition. So we have to enter international competitions to do, for example, parts of GCLEF or parts of the telescope, like the mount or the enclosure. So we have to get prepared for those things, and we are doing that. The one part that we hope to participate in the bid is the enclosure of the telescope, for example. We have already taken part in the competition for building the optical bench for GCLEF. So we will be trying, and we have someone that is the industry liaison. There's one person that takes care of just the interface between the GMT-Brazil office and the industry. So we are actively pursuing that. I didn't say this during the talk. Sorry.
Thank you.
More questions? No more questions?
Just a compliment to the answer to Alessandro, that the same as Andy said about GCLEF. So we have ETC for GMACS available in the Texas A&M website, so you can play with them. And I hope it's correct at maximum factor of 2.
Magnitude. Okay, so before we break for coffee break, I ask you guys for just a second, because we are going to have some
or maybe 2 minutes.
Words to say.
Yeah.
And before that, let's thank again our 2 speakers.
Okay, we still have a very important class to attend, which is Dan Jaffe's class. But we would like to start our acknowledgement, just do the half of our acknowledgements to the employees, because they leave at 5 o'clock. So they won't be here for us to acknowledge them. So I'd like just to spend a few minutes thanking the people who really made this happen and who were really helpful in arranging everything here for us. Do they know that they have to come here? Because Please, Luciana, Roseli, Yoko, are you there? Could you please come here so that we can help you? Yara, Edger, could you come? You know, these are the people who made this meeting be very successful. Please come to the front. Let's just thank them. Edger, please. I think that it's very, very nice that everything went very smoothly, and thanks to our collaborators. Yeah, Yara and Edger are from IEE, which is this building here, this place. Thank you very much. Okay. Picture. Okay, thank you very much. Okay. Okay, now coffee break. Yeah.